Okay. Frequency, wavelength, and the speed of light. Today's topic. So, first of all, C is a constant, and it stands for speed of light. And what is it? 3.00 times 10 to the 8th meters per second. So C, again, speed of light. Next thing is something called frequency. Frequency gets stood for by, it's like a little V with a hook. And when we have frequency, we have something per second. And what it is it's waves per second. Not a coincidence that it's per second for the speed of light. And likewise, the last thing is something we use lambda to stand for. Kind of looks like a stick figure without a head or hands. So that's equal to the wavelength. And that is measured in meters. So again, this is frequency. This is wavelength. And C is the speed of light. Okay? Now, what do these things mean? What it means is this. Frequency talks about just that. How frequently a wave passes a given point. So for example, if I was to draw two waves, one that does this, and we'll make this right here the 0 point on it. And then we drew another wave that looked like this. So we'll draw the 0 line. Etc. So we keep going. If we were to look at these two waves and look at the frequency, well, you can see how this one, right, passes and completes. So up and down is one complete wave. So you get 1, 2, 3, 4, 5, 6, like 6.5 waves on this one. Whereas here we're only getting one full wave to here and another half. So therefore the one that has a greater frequency is the top one. So why don't we give that a label? We'll call that wave A, and we'll call this wave B. So wave A has the greater frequency. Now, wave B. Wave B doesn't have the greater, it has the lesser frequency. But if you look at the wave and how long it is, I mean, this one might be, I don't know, 3 centimeters, 4 centimeters, whereas this one's, probably 20 centimeters. And so to get from the beginning back to it is one full wave, one full cycle we call it. And so the letter B is the longer wave length. Now why does that matter? Well, it matters because we have an expression and it is this. C equals frequency times wavelength. And the reason it works is this. We said C up here is measured in meters per second, right? And that is equal to the frequency, which is measured in per second. And it's specifically waves per second. And then we said that the wavelength is in meters. So this is a constant, right? And so what ends up happening with these calculations is we end up calculating using a constant C for either frequency or wavelength. Now let's talk about a couple of things that happen here. Okay, you can see in our version our waves A and our waves B. Well, in order to get more frequency, here I had to sacrifice wavelength. Here, in order to get longer waves, I had to have less frequency. So one of the things I want to point out in this very first introduction to this is that they are inversely related. So frequency and wavelength are inversely proportional. Meaning, if you increase the other one must go down. Now let me tell you why, what's the real world application of this? Well, the real world application of this is AM and FM radio is really the best way to explain it. So AM radio means amplitude modulated. Now, in a wave, we have different points and different things that we look at, okay? You have a top of the wave, which is called the crest. You have the bottom, which is called the trough, right? And then you have wavelengths that are through here. And you have something called the amplitude. Now, the amplitude is how high or low the wave is. So that's called the amplitude. As we increase the amplitude, we get longer distance. So therefore, AM radio equals amplitude modulated. When we have things that are amplitude modulated, we're looking for longer wavelengths. This is why when you're in, Kentucky, you can pick up 760 WJR on the radio. But FM, on the other hand, is frequency modulated. What does that mean? It means this. So frequency modulated means that we go for more waves. Now the byproduct of more waves is that we get more energy. So this is why on FM radio you get things like Justin Timberlake and Destiny's Child, and you get all these things that have a lot of waves and thus require a whole lot of energy. So again, this is frequency modulated. And again, the trade-off is this. 760 WJR, I could pick it up all the way down to Kentucky. But with FM radio, if I leave and try to go to Kalamazoo for the day, I can't pick up 95.5 in Kalamazoo. I got to pick up their version of an FM radio signal because the wavelength is shorter due to the need for the synthesizers and all the high energy instrumentation. So again, that's a general idea of this idea of relationship between speed of light, frequency, and wavelength.